Imagine that there are n items, each one of them has a price and the amount you need of it, and you want to know at what price you can get them. Easy, you just do the sum of the amount times the price for each item. But before you buy, you hear that there are special offers. An offer consists of the amount of each item and its total price. For example, this offer means that for $12, you can get the item 0 once, the item 1 once, and the item 4 twice. Here you stop and think, can I buy the items I need for a lower price than buying them individually? Knowing that because of car space, you cannot buy more items than what you need. And this is what this problem about. We have an array price of length n where price of I is the price of the item I, an array needs of length n where needs of I is the amount you need of the item I, and an array special of offers where each offer has a length of n plus 1, and for the amount of each item, and the last cell for the total price. Starting from this input, you need to find the lowest possible price to buy all items you need, knowing that you cannot buy more items than you need, even if it would reduce the price. And you can take the same offer multiple times. For example, we have 3 items. Their price are $10, $5, and $7 respectively. And we need the item 0 twice, the item 1 4 times, and the item 2 once. We have 2 offers. The first one, the first item and the second item once for $12, and the second offer, the second item and the third item twice for $10. The minimum price that we can get is $41. We first take the first offer twice, remaining needs are the second item twice and the third item once. We just buy them individually. We could take the second offer, but we would buy more items than what we need. Not allowed. And the total is 2 times the first offer, 2 times 12 is 24, plus 2 times the price of the second item, 2 times 5 is 10, plus once the price of the third item, 7, we get 41. This problem kinda reminds us of the unbounded knapsack problem. Let me tell you why. By the way, unbounded knapsack problem is the problem of finding how many times we should take each item to maximize the total value without exceeding the total weight. We solved it before in this channel. I suggest you to watch the video before continuing this one. In unbounded knapsack, we have items that we can take 0, 1, or multiple times. In this problem, same thing but with offers. In unbounded knapsack, there is a condition to take an item, is that its weight doesn't exceed remaining available weight. In this problem also, there is a condition to take an offer, is that its amounts don't exceed remaining needed amounts. It doesn't make us buy items more than what we need. In unbounded knapsack, at each stage, we can have multiple possible items to choose from, and we use recursion to try all possibilities and take the one that gives us the best total value. In this problem, we can also have multiple offers to choose from, and we use recursion to try all possibilities and take the one that gives us the best total price. In unbounded knapsack, we have an initial value, and each time we recursively try taking a new item, we check if it gives a better result than the actual value. In this problem, we also have an initial price, and each time we recursively try taking a new offer, we check if it gives a better result than the actual price. A lot of common points. Let's try to go from the solution of unbounded knapsack and produce a solution to this problem. The solution to unbounded knapsack was this one. The initial value is 0 because we didn't take any item. And for each item, we start by checking if we can take it, if its weight doesn't exceed our remaining available weight. If it's the case, we check if it gives a higher value than our actual max value. This is why max value becomes max between its actual value and the value of the item plus the best value we can get after taking it. Max because we want to maximize the total value. At the end, we just return the max value we found. Let's try to apply the same logic for our problem. First of all, unlike the unbounded knapsack problem, in this problem we want to minimize the result, not maximize. so we will use min price and min function when comparing two results. What is the initial min price? Take some seconds to think about it. The initial max value was the value when taking no items, so the initial min price here is the price when taking no offers. And when taking no offers, we have no choice other than buying items individually at their full price. And the total price can be calculated like this: the sum of the amount of each item multiplied by its price. Now we start trying possible offers. For each offer, we first check if it's possible to take it. Remember that we cannot take an offer if it makes us buy items more than what we need. So an offer can be taken if the amount of each item I in it doesn't exceed the amount we still need of the item I. In other words, for each item I, offer of I must be smaller than or equal to needs of I. If we can take the actual offer, we have to try it and see if it gives a lower price than the actual min price. We have the actual min price and the price when we take the actual offer, which is the price of the actual offer plus the best price we get after taking it, that we can calculate recursively. We compare between these two and take the minimum. But, important detail, when calling recursively, we don't have the same needs, because when we take an offer, our needs decrease depending on what items does the offer contain. So before calling, we need to calculate the new needs, which can be done by subtracting the amount of the item I in the offer from the needed amount of the item, to get the amount we still need of each item. In code, new needs is needs of I minus offer of I for each item I. Also, the price of the offer is in the last cell. In Python we write offer of -1. So we write min price becomes the min between its actual value and offer of -1 plus the result of calling recursively with the new needs. After doing so for each offer, we return the min price we found. And we solve the problem by using the solution of another problem. This is why my advice is always to practice on a lot of problems to have the opportunity to discover a lot of techniques and patterns that you can reuse for other problems as we did here. Last thing, even if we do different offers choices, we can reach the same state of needs, which means that we have overlapping subproblems. Instead of repeating the same work every time, we can store the result of each subproblem we solve in a lookup table, and before solving a subproblem, we first check if we didn't solve it before. It's called top-down dynamic programming, memoization. We can apply it to our problem to reduce execution time. For that, we add a lookup table that we initialize, and we check if we didn't solve the actual subproblem. We check if the key already exists in the lookup table. The key in this problem is the array of needs. It's the only parameter that changes, so it's the only thing that characterizes a subproblem. And to be able to hash it, we convert it to a string. So if the array of needs as a string exists in the lookup table, it means that we solved this subproblem before. We don't need to do it again. We directly return the result that we stored. We return lookup of str of needs. Else, we solve the subproblem normally. But before returning the result, we store it in the lookup table. We assign it to lookup of str of needs, to be able to find it later. And we're done. Here is the execution time in LeetCode before and after applying memoization. We're done with this problem. I hope that you understood the logic behind the solution and how we used Unbounded knapsack problem to solve this one. If you want to support the channel, like and subscribe, or you can buy one of the courses in description. See you in the next one.